Artificial intelligence infrastructure conversations often begin with a number. A company announces a campus, a utility talks about megawatts, a developer points to contracted power, planned capacity, or generation somewhere in the system. Those numbers matter, but they can also mislead, because a data center does not run on power that exists somewhere. It does not run on a headline capacity figure. It does not run on a procurement slide. It runs only when usable electrical service reaches a physical site and can be energized under reliable operating conditions. That is the governing question for this episode. Not how much power exists, but how much power can be delivered here, by this date, through this grid, while the system still meets its reliability obligations. That distinction changes the artificial intelligence power debate. It separates nominal power from deliverable power. It separates contracted or announced supply from energized load. And it explains why some public capacity claims are less complete than they sound. Power becomes useful only after the delivery system can forecast the load, study its location and timing, test the path, identify required reinforcement, execute utility and regional planning, connect the site, and energize the usable load. Until then, the number may be real in one sense, but not yet operationally useful. Consider what happens when a proposed artificial intelligence campus becomes a serious load claim. The system cannot treat it as a vague demand for electricity. It has to ask specific questions. How large is the load? When is it expected to arrive? Where is it located? Is the demand steady or variable? What does it do to existing demand? What does it do to forecast demand? What reliability implications appear when a large block of new load is added to a specific part of the system? This is why load forecasting matters. In the PJM region, data center-driven load growth has entered formal load forecasting and planning materials. PJM is not just reacting to a press release. It is incorporating expected large load growth into planning assumptions, study years, zones, and reliability analysis. That does not mean every forecasted load is ready to serve. It means the load has become visible to the planning system. A proposed campus becomes a planning input, and once it becomes a planning input, the question moves from commercial ambition to electrical deliverability. The facility may have a power story. The grid still has to determine whether that story can become service. A forecast is not a delivery commitment. This is one of the most important distinctions in the entire episode. Forecast demand means planners expect load to appear. Planned capacity means the system may be preparing resources or infrastructure around future conditions. Network deliverability means the grid path has been studied under relevant operating and reliability assumptions. Completed reinforcement means the required physical and planning work has moved from need to execution. Energized load means the facility can actually use the power. Those are different states. Artificial intelligence capacity claims often blur them together. A number can describe announced capacity, contracted power, forecast demand, studied load, reinforceable load, connected load, or energized usable load. If those states are collapsed into one headline, the claim becomes operationally ambiguous. PJM load forecasting is powerful evidence because it shows that data center load is visible in the planning process. But forecasting does not by itself prove that every requested load can be served immediately. It is the beginning of a delivery question, not the end of it. Recognizing future demand is not the same as having a completed path. The next step is deliverability. Deliverability asks whether power can move through the transmission system to the relevant load under required conditions. It asks whether the system can serve that demand reliably, not merely whether enough electricity exists somewhere else. This is where regional transmission expansion planning becomes central. PJM's regional transmission expansion planning evidence connects large load growth to heavier regional transfers, deliverability analysis, reliability tests, and reinforcement planning. That is the spine of the argument. The point is not simply that data centers use electricity. The point is that large concentrated load can become part of the regional planning problem. NERC supplies the broader reliability frame. It treats rapidly connecting data centers and other large commercial or industrial loads as a challenge for demand forecasting and bulk power system planning. That does not prove a single project delay. It does not prove a universal national pattern. But it does support the claim that fast large load growth has to be planned and studied as a reliability issue. Available generation and aggregate capacity are therefore incomplete answers. If the grid cannot deliver power to the requested place, at the requested time, under reliable conditions, the power is not useful to that facility yet. When concentrated load enters the planning system, reinforcement may become part of the real project. That reinforcement can take different forms. It may involve transmission upgrades. It may involve substations, switching stations, high-voltage equipment, voltage support, protection systems, rights-of-way, or network enhancements. It may involve utility sequencing and regional planning decisions. The important word is may. Not every artificial intelligence project requires every category of upgrade. Not every utility project is caused only by artificial intelligence, and illustrative transmission or substation examples should not be treated as proof of a universal artificial intelligence bottleneck. Their value is more specific. They show what delivery work can look like when a large load has to be connected through real infrastructure. A data center does not connect to an abstract pool of electricity. It connects through lines, substations, switching equipment, transformers, protection systems, and operating rules. Those systems have locations, they have limits, they have planning cycles, they have construction schedules, so the infrastructure behind the power number matters. The useful question is not just whether a facility has found power, it is whether the delivery system has found and completed a reliable path. After planning comes execution. This is where the schedule can stop being controlled by the artificial intelligence developer's preferred timeline and start being controlled by the delivery system's timeline. Required upgrades have to be planned, approved, sequenced, built, connected, and energized. Utility work has to coordinate with regional planning obligations and reliability requirements. A site may be commercially ready before the electrical path is ready. There are also unresolved implementation signals around transformers, switchgear, energization queues, and service queues. Those signals should be treated carefully. Transformer lead times are relevant background because large power transformers can be slow infrastructure to procure and manufacture. But the current source record does not support the claim that transformer scarcity is the decisive artificial intelligence deployment bottleneck. Switchgear is even more limited in this record. It can be named as an unresolved equipment category, not as a proven general constraint on artificial intelligence campuses. Energization and service queues are also not proven here as general blockers. They remain important signals for future source work, not the foundation of this episode. The stronger point is broader and better supported. A power agreement does not energize a site. Generation does not automatically create deliverability. The project is constrained by the delivery system's ability to complete the required path. This is why public artificial intelligence capacity claims can fail without being false in the narrowest sense. A company may announce a large capacity target. It may contract for power. A utility may forecast load. A regional planner may study that load. A reinforcement plan may identify needed upgrades. A site may become connectable. Later, some portion may become energized, usable load. Those are all different states. Announced capacity is a strategic claim. Contracted power is a commercial position. Forecast load is a planning assumption. Studied load has entered system analysis. Reinforceable load may be possible after upgrades. Connected load has a physical service path. Energized usable load is what actually powers the facility. If a single megawatt number moves across those categories without explanation, the audience cannot tell what has really been achieved. The most memorable distinction is simple. Power on paper is not the same as power at the site, and power at the site is not real for operations until it can be energized reliably. Credible artificial intelligence infrastructure planning has to make the delivery layer visible. It has to include geography, where the load actually sits. It has to include timing, when the load is expected, and whether the delivery path can be ready by then. It has to include transmission deliverability, whether the grid can move power to the site under required conditions. It has to include reinforcement, what lines, substations, switching stations, voltage support, protection systems, or network upgrades may be needed. It has to include utility execution, who has to plan, approve, build, sequence, connect, and energize the required facilities. It has to include reliability, because serving a concentrated load cannot be evaluated only as a commercial transaction. It has to include phased energization and uncertainty, because a campus may become useful in stages rather than all at once. This does not make artificial intelligence infrastructure impossible. It makes the planning standard more honest. A credible plan should say not only how much power is being pursued, but what state that power is in. Is it announced, contracted, forecast, studied, reinforceable, connected, energized? The answer determines how real the capacity claim is. The real constraint is not always generation, it is not always tariffs, it is not always equipment, and it should not be reduced to one dramatic bottleneck unless the evidence supports that claim. For this episode, the useful unit is more precise: deliverable, reliable, energized power at the required location and time. That is the unit that matters for artificial intelligence infrastructure. A megawatt is not operationally meaningful just because it exists somewhere in the system. It becomes meaningful when the grid can carry it, transform it, protect it, switch it, connect it, and energize it for the site that needs it. PJM shows why data center load can become part of formal forecasting, transmission planning, deliverability analysis, and reinforcement pressure. NERC shows why rapidly connecting large loads belong inside reliability planning. Utility project examples show the physical reality behind the planning language while remaining illustrative rather than universal proof. The conclusion is bounded, but strong. Artificial intelligence capacity is not only a question of how much power can be named, procured, or promised, it is a question of how much power can actually be delivered. Until that delivery path exists, the number may describe ambition, demand, planning, or procurement. It is not yet useful power. If you found this useful, subscribe to Quantum Convergence, AI, for more evidence-driven analysis of the systems shaping artificial intelligence.